Hi everybody, we're going to look at Unit 3 in our weekly starter video. The first thing that we're going to do is take a look at our ISN pages. We'll look at the table of contents for Unit 3, and then we'll also look at 3.01, 3.02, and I threw a page in there for some of our special trig functions. We're going to take a look at those ratios. You might remember them from SOHCAHTOA or sine, cosine, tangent. Then we're going to take a look at the directions for the lab. Make sure that you guys understand what the expectations are for the lab at the end of the week. Here's our table of contents. Unit 3 is not super abundant in the ISN, but there's some good information there. The first one that you're going to do is the graphing labels from 3.01. Then we'll do 3.02 with the graphs and data relationships. 3.0 after that, we'll do these trig functions. And then for 3.06 and 3.07, I went ahead and let you guys do it on your own. So if you notice, that's why they're over here on our table of contents, because it will be on your side of the page. So my side will have 3 sections, your side will have a few more than that. It'll have something for 3.01, 3.02, 3.06, and 3.07. You're also welcome to use your side for some of your notes during the lab process if you would like. You're not limited to just those. All right, so graphing labels. This is a picture of a graph, and you're going to have to actually, you'll end up taking a quiz on this. So little tidbits of vocabulary here. The axes for these particular ones, the picture in here, you've got number 2 is an axis and number 1 is an axis. And if you notice, those lines point straight to the axis right in between the tick marks or the hatch lines. Data points, 6 represents data points. And then you've got the tick marks. Let's see here, that would be number 3. And the trend line is number 7. The thing that you want to always remember about a trend line is that it really is just a trend. This is not a connect the dots kind of line. When you're looking at data and you're collecting data, you're going to have issues where your data might not be precise, or you might not be as accurate as you would have expected because there was something wrong with the equipment or whatever the case may be. So just remember that your trend line is truly that pattern of your data that you would expect, not the exact like zigzag between all of your data points. So this particular trend line is a great example because for the most part it's pretty close and it does go through a few points, but it also misses a few points. So this is a good example of a trend line. All right, and then you also have your labels for number 4 there. Oh, and your title for number 5. So you're just going to want to go through and label all of these. I put numbers down at the bottom of mine and just wrote what they were because I felt like writing on the graph got a little jumbled. But again, this is yours. You can do it however it makes sense to you. The next one we did are a couple of data relationships, and this is something that you might reference back to as we're doing some different experiments, and we're really looking at what type of relationship do these concepts have. Things like velocity is going to be a linear relationship, right? As you increase the number of or the amount of distance that you go, you're going to increase your speed or your velocity. However, something like force is not necessarily linear depending on what variables you're comparing it to. So at any rate, we want to be able to identify when we look at a graph some of these different data relationships. So what I did to make this one, and this was one that I had a little bit more fun with, got a little creative, but I took 2 pieces of paper and glued them together. And then I went ahead and folded them in I guess that's fourths, but it's kind of a funny fourths because I folded the outsides into the middle so that they overlapped. And then I just cut the slits right here and right here. And those slits allowed me to have 4 flaps. And then I drew a picture of the graph on the outside, and I wrote the type of relationship, or the type of graph, or the type of relationship on the inside. And then I went ahead and also wrote some of the patterns. So if you notice when you're looking up here for my linear, I have y equals x and y equals mx plus b. That's that familiar slope-intercept form of an equation that you probably have had ingrained in your brain at some point during an algebra class. But those are both acceptable forms of a linear relationship. So those are both patterns that we have. Same with the quadratic, and then the exponential is down here at the bottom, the y equals b to the power of x. And then the inverse is y equals 1 over x. Now, of course, there could be more stuff in there, right? I mean, we could have, you know, b to the power of x minus 4. It just kind of depends on that relationship, but that's kind of the core relationship that you're looking at for an exponential function. So our special trigonometric functions. This is something that we are going to use all the time in physics class, all the time. And basically what this is saying is that right triangles have ratios. And so when you have a right triangle and you know your angle theta, and that's what this little symbol here is it looks like a pokeball almost, right? Almost, not quite. But it's the Greek letter theta. So when you have the sine of theta, it's going to equal the opposite over the hypotenuse. Now this sine function only works when you're working with a right triangle and when you are dealing with a specific angle. You can look at the opposite leg and divide it by the hypotenuse. So you always have to be set up well when you use SOHCAHTOA or the trig functions, and you need to make sure that you kind of stop and analyze to make sure you're using the proper function for what you want to find. So this is like maybe you know the hypotenuse and you know that angle theta, but you want to find the length of that opposite leg. This is where you might use sine. If you are trying to find the length of the hypotenuse, but you know the adjacent leg, you could go down here and use cosine of theta. And so these trig functions we'll use a lot more. If you're not familiar with these already, I don't want you to worry because we will get you there. But the trig functions are going to be really important for class. We're going to use them to figure out direction in 2 dimension. We're going to use them to figure out forces and all sorts of stuff. So the cosine of theta is equal to the adjacent leg divided by the hypotenuse, and then the tangent of theta, or tan of theta, is equal to the opposite divided by the adjacent. So if you notice, there's, as long as you know that angle or one of the sides, or you know both of the sides and you want to find the angle, you can use one of these functions. So it works, there's a combination basically for everyone. And I did, this right here was one piece of paper, and this is the long leg. So this side here is the 8.5 inch side, and this is the 11-inch side. But I just folded it into thirds and then cut tabs on the little flappy part and made it this way so that you can see the SOHCAHTOA, and it's an acronym for helping you remember it. But SO is sine over opposite, and then divided by hypotenuse. So that's where you get the SO. K comes from adjacent over hypotenuse. Promise that's a P. And then the TOA comes from opposite over the adjacent. So hopefully that makes sense. And then of course I drew the triangle. I feel like I'm a little bit more of a visual person sometimes with things like this, and I have to like actually visualize that triangle up against where I'm working in the situation. So that's why I put the triangles in there, because hopefully that will help another visual person. All right, so our lab. We're going to look at this lab, and really this is going to be more of a practice of graphing and gathering data and precision and getting accurate measurements, things like that. But we are going to answer a great question. The idea is that you pour yourself a cup of coffee and you're about to add cream, but all of a sudden you get pulled away for 15 minutes. So you need to decide, do you add the cream now before you leave, or do you let it sit hot and then add the cream when you get back so that your coffee stays hot as long as possible? So we want to know which one changes the temperature faster, hot water mixed with cool or hot water left alone and then cool water added at the very end. So you're going to go ahead and boil some water and pour it into a separate container. You're going to observe the temperature of the water every 30 seconds for 15 minutes. So there should be 30 data points. You're going to repeat that process, but this time you're going to add cold water after just 2 minutes. And then you're going to repeat it again, but now you're going to add cold water after 12 minutes. So the very first one is our, this is the one that we're just going to see what would be expected if you left it alone, right? Our second trial here and our third trial are going to be the ones where we have that variable. So now we're going to test it to see which one is going to have the biggest change and which one's going to end in the highest temperature. So you're going to want to write a hypothesis for this. A great way to write a hypothesis is using the if-then statement. So if you say, well, if you add hot water fast or earlier, then the water will stay hot longer. So the questions that you're going to answer with your hypothesis is what's going to happen to the temperature of the water and which one holds the heat best, which one will stay hot the longest. So some of the materials that you're going to need, there's the student guide, graph paper, lab guidelines. Those are all found in the lesson. From your kit, you're probably going to want to grab the funnel, just for pouring your water, a stopwatch, safety goggles, a thermometer, and a 250 milliliter graduated cylinder. That's where the funnel comes in handy, especially dealing with boiling water. You really don't want to get too close to that. So, and you're going to pour it into that tall, skinny cylinder that you have. From home, you're going to need water, some sort of oven mitt or pot holder, coffee mug that's at least large enough for 250 milliliters, and a stove-safe or microwave-safe container for boiling water. Basically, all of that means that you just need boiling hot water. I know lots of people have different ways of getting their hot water, so. Here is your data table. Now, the data table that you have actually stops early, but you want to go ahead and fill it in so that you get data every 30 seconds for 15 minutes. So that's 30 points of data. And you're going to get it for 3 different situations. The first situation is the temperature of the hot water alone, and that information is going to just fill this column here. The next one is the temperature of hot water when cold water is added at 2 minutes. So you're probably going to see a big change right about here in the temperature. And then the next one is the temperature of the hot water when the cold water is added at 12 minutes. So again, you may see a big change here, assuming that there's a change to be had at that point, right? Because if the water is the same temperature as the cold water by that point, there wouldn't be a huge change. Or maybe not any at all. So you're going to go ahead, and the graph is a really big part of this lab. So be sure to label your X and Y axis. You want to include units, and you can just do that by the title. So you can say like temperature, and then put Celsius at the end, right? You don't have to try and squeeze all of the title or the label into each one of the little hatch mark labelings. But you do need to include the units. You want to identify your variables. So which one's independent and which one's dependent? The independent one is the one that's just going to keep going on no matter what. The dependent one is the one that's going to change dependent on your independent variable. You want to make sure that you use a scale that works. So it's going to be really important to gather all of your data before you do that graph. And then you can figure out, okay, I have, 100 lines on my graph and I have 30 sets of data. You can do three lines for every degree at that point, but if you did 4, you would run out of room. So it's really important just to know what your limitations are. The other thing is that once you pick your scale, you have to stay consistent. So if you're jumping by 2 and you're doing 2 degrees, 4 degrees, 6 degrees, 8 degrees, you can't all of a sudden do 9 degrees, right? You've got to keep that scale consistent. The next thing is that you need to plot all 3 trials on the same graph. So you're going to use a different color for each trial. You do not need to make 3 separate graphs for this. If you just grab some coloring pencils or colored pens, you can do the graph in different colors for each one of your trials. But you do need to have a key that tells me which color you used for each trial so that I can tell as I'm looking at it which goes to which set of data. And then of course your graph needs a title. Every good graph deserves a title. All right, so if you have any questions, please don't hesitate to ask. If not, I will see you in class on Tuesday.